Hello, everyone. Today we are going to talk about elevator problems. I love elevator problems. AP loves elevator problems. So we all need to learn to love elevator problems. So up until now, we have pretty much always had normal force equaling gravitational force. If we're working in just a normal 2D plane with no trig, no finding angles, no inclined planes, if we're just working in like normal XY world, we've always had it equal. That's not going to be the case anymore because riding an elevator, your body is accelerating and you're moving in the direction your body's accelerating, either positive or negative or whatever. So we have some situations where your weight is not actually your weight. If we have zero acceleration here, your normal weight is just your weight. If we're accelerating upward and moving upward though, you're going to have a greater than normal weight. So if you stood on a scale in an elevator, your weight would read greater than that. Now, let's say you're moving upward, but your elevator's slowing down. Your weight is actually going to read less than your normal weight. And then finally, if that elevator cord breaks and your scale drops to zero, you're in trouble because your acceleration is equal to g, which means you are in free fall. We're going to jump into some of these and go over some of the terms that I'm using. So one thing I want to point out, I'm going to use the term apparent weight. So this is a property of objects that corresponds to how heavy an object appears to be. Now, your apparent weight might differ from your ordinary weight, like I said, depending on how the force gravity is balanced or not balanced to another force. So, for instance, if I'm standing on a scale in an elevator and I'm accelerating upwards, those forces are not going to be balanced. If I'm standing on a scale and I'm accelerating downward in an elevator, because my elevator is moving, they're not going to be equal. So the term apparent weight is really me just saying, what does a scale read? Or what does your body feel like you weigh? Your actual weight never changes. This is going to sometimes be called your ordinary weight. Your actual weight, it's just Fg equals m times g. That does not change because your mass isn't changing and the strength of the earth pulling on you doesn't change. Now, eventually that small g value will change. We'll talk about if you go up on top of mountains and stuff like that. But for right now, our understanding of where we're at, that small g is always 9.8 or 10 if you round it. Let's look at some actual problems of how this works out though. So we've got a 40 kilogram person sitting on an elevator. The elevator has a mass of 500 kilograms. And the elevator starts to accelerate upward at 2 meters per second squared. We want to know what's the person's apparent weight at this time. Now, thinking about this, I'm going to draw a force diagram, just like I talked about in the unbalanced forces notes. We're going to have force gravity downward, and we're going to have normal force upwards. We're going to make up our positive direction. So thinking about this, if my person's just sitting there and the elevator's not moving, gravitational force is going to be equal to normal force. However, the second the elevator starts to accelerate upward and you're moving upward, then you're going to have some unbalanced forces. So I'm going to say the sum of my forces is equal to MA, which is equal to Fn minus Fg. If we were just sitting still, this MA would be equal to 0, but we're not sitting still. We've got some acceleration. We're just looking at the person's weight, so we don't need to worry about the elevator's mass right now. So I've got 40 times my acceleration of 2, which is equal to Fn, because apparent weight is actually Fn. That's what it's asking me for, minus 40 times 9.8. So 40 times 9.8, this gives me, this is 80 first off. This gives me 392 newtons. So if I were just sitting still on the scalar reading, it would read 392 newtons. But since I'm accelerating upwards, then you have to add that 392 and that 80 together, which gives me a normal force of 472 newtons. So if I'm standing on my scale in an elevator and accelerating upward, my weight reads more than my gravitational force. So if I were to actually edit this force diagram, I would need this line to be longer because my normal force is greater than my gravitational force. All right, let's keep looking at this idea. got another example. So now there's an elevator with a total mass of 1,600 kilograms. It's going down at 12 meters per second. Over 42 meters, it comes to a full stop. We want to know what was the force of tension on the elevator during this event. So we're not looking at the person inside the elevator now. We're looking at the whole elevator as a whole. So my system is the entire elevator. We still have a gravitational force downwards, but now we're looking at the elevator as a whole. So we have a tension force upwards. And we want to know what was the tension on the elevator as it was accelerated. Now, looking at this, I have some kinematic values given to me. We're told that our initial velocity is 12 meters per second. We're going to come to a full stop, so our final velocity is 0. We know that our change y, we're going down, so our change in y is going to be negative 42 meters because it's moving downwards. And we're going to need to know our acceleration. Like in the first unit, when we were switching between the x and y directions and time was our ability to do that, to switch between kinematics and forces, acceleration is our thing that allows us to switch back and forth. So I think as you do these problems, you'll learn that acceleration allows you to go between kinematics and forces. So I'm going to use my my third kinematic equation to solve for this acceleration. 0 squared, 12 squared plus 2a times negative 42. So this gives me 0 equals 144 minus 84a. I'm going to move the 144 to the other side, which gives me, this is a 42, that's really hard to read, sorry, which gives me an acceleration of 1.7 meters per second squared, which you need to check out with yourself. Okay, if I'm moving downwards and I'm slowing down, my acceleration has to act in the opposite direction. So getting a positive acceleration here is a confirmation to me that I'm doing my problem correctly so far. It's 1.71. Technically, I'm going to add a 1 there. So now we can go and do our forces. So sum of forces is equal to ma, Newton's second law, and our force tension goes up and our gravitational force goes down. Our mass of our elevator is 1,600 kilograms. Our acceleration is 1.71. We don't know FT, and force gravity is going to be 1,600 times 9.8. I don't want to do these parts separate, so I'm just going to move the 1,600 times 9.8 over first, so I can just plug it all in my calculator at once. So I'm going to do 1,600 times 1.71 plus 1,600 times 9.8. This gives me a tension force of 18,416 newtons. Which checks out because I should have a greater force tension than I do force gravity, and the force gravity is 15,680 newtons. So since I'm slowing down, moving downwards, I should have an acceleration upwards, which means my tension force should be greater, which when it is greater, that checks out for me. Again, elevators are so popular in AP Physics 1. I want to emphasize to you guys that if you know how to do one type of problem really, really well in this unit, it is understanding how these problems work. So much, we're actually going to do a lab using this. So keep going. Let me know if you have questions. I'm here to support you guys.